Hello, everybody. It's a real pleasure to introduce you Alexander Murray Wright from the University of Michigan. He's an awardee of our MCA 2021. Here, his PhD in the University of Chicago, and now he's an assistant professor at the University of Michigan. He's a Canadian and he's from Toronto, I think. So it's a pleasure to introduce him, and he will talk about random surfaces of large genes. Please, Alex,
okay, thank you.
Go ahead. You can share your screen.
Okay, thank you for the invitation and the opportunity to speak here. And of course, I'm grateful to the MCA for the honor of being awarded the MCA Prize. I'm going to talk about random surfaces of large genus. Some of this will be joint work with my colleague Mike Lipnowski, who's at the University of McGill in Canada. A lot of it, though, is just going to be a very broad overview of the field and the context and related work. So I'm not going to come to my own work until at the very soonest halfway through the talk. And I should say throughout the talk, please ask questions whenever you have them. Just unmute yourself and feel free to speak up. I'm very happy to get lots of questions. The basic question that I want to examine in this talk is, what does a typical surface of large genus look like? And I haven't defined typical. That will come later in the talk. There are different definitions of typical. But the idea is you want to have some picture in your mind of what to expect a large genus surface to look like. And probably what you have in mind if you think about a high genus surface is a picture of this, a fairly linear picture, just sort of a connect sum of tori all strung out in a line. And that I think for most people is the only picture in their mind of a high genus surface. It's the easiest to draw. And it has various features, like its diameter is linear in genus. If you look at the number of curves of length, say at most 100, that also grows linearly in the genus. It's easy to cut in two. You can just cut it halfway and get two equal pieces. But actually, if you remember nothing else from this talk, please remember this is a terrible picture. It in every way is not generic. Typical high genus surfaces don't have any of these properties. So this is actually an extremely misleading picture of a high genus surface. And I'll tell you throughout the talk various ways that it's misleading. So you can keep this picture in mind as essentially a picture to refute, something to contrast with. This is atypical. But before we go any further, I should tell you what sort of surfaces we're interested in. So I'm interested in hyperbolic surfaces. So that's constant curvature -1. The universal cover is the hyperbolic plane. And there are various ways to build these surfaces, as we'll see. A nice starting point is via pants. So a pants is a sphere minus 3 disks. And given any 3 positive numbers, you can actually build a unique hyperbolic pants. So the 3 cuffs, those 3 boundary curves are called cuffs in this context. The 3 cuffs of the pants are geodesics of those lengths. And then you can glue together pants as long as you make sure that the cuffs have the same length. So maybe for now, just for simplicity, we'll pick one constant and make all the cuffs of all the different pants equal to that constant, so we can glue them however we want. And here I've illustrated an example with 2 pants. And if you glue the red cuff to the red cuff and the blue cuff to the blue cuff and the green cuff to the green cuff, then you get a genus 2 surface. But you could glue together more pants to get a bigger genus surface. And of course, each pants by definition has 3 cuffs. And so the gluing pattern is given by a 3 regular graph. So a graph where every vertex has 3 edges, leaving it. And of course, the vertices correspond to the pants and the edges to the cuffs, or really the pairs of cuffs that get glued together. And the number of edges and vertices in genus are all transparently related to each other. You can calculate any one from any other one. The main point I want to make is that as the number of edges goes to infinity, the number of vertices goes to infinity, and the genus goes to infinity. So there's no competition what large means. You know, edges, lots of edges is the same as lots of vertices, and that's the same as lots of genus. Okay, so, you know, motivated by that, given that we can use a 3 regular graph as a gluing pattern to get a high genus surface, maybe for the first part of the talk, we'll switch to a more elementary question and review what's known about the question, what does a typical large 3 regular graph look like? And for large, so remember from the previous slide, the number of edges is 3/2 times the number of vertices. So large either means large number of vertices or large number of edges. There's no difference. And this is an easier question because there's a natural and easy notion of typical. For any number of vertices, there's a finite number of 3 regular graphs with that many vertices, and we can look at the uniform probability measure on them. So on a fixed number of vertices, we can look at a uniformly random 3 regular graph. And I should say that you could use a D regular graph for any D at least 3, and everything I'm going to mention works for any D. I'm just specializing to D equals 3 for concreteness, and because has the most transparent connection to random surfaces, but it doesn't make much difference. You can look at regular graphs for any fixed D and let the number of edges and vertices get big. So in the first part of the talk, I'm gonna review what's known for this question. So one of the easiest results to appreciate is not only are these graphs connected, they actually have diameter that's logarithmic in the number of vertices or the number of edges. So this goes back at least to 82. The diameter is typically about log base 2 number of vertices. And already that gives you an inkling that the linear picture of the surface we have might be non-generic because that had linear diameter. And at least for typical 3 regular graphs, the diameter is actually logarithmic. So somehow they're pretty highly connected. They have pretty small diameter. And this is basically as small as you could dream of it being for a 3 regular graph. So the diameter is quite small. To improve our understanding, we could ask about the expected number of I cycles. So an I cycle is just a loop of length I. So you follow edges until you come back where you started. And if you come back in I steps, that's an I cycle. And then you could say, well, if say I asked the number of 3 cycles, so that's the number of triangles that my 3 regular graph contains. You can ask, you know, as I increase the number of vertices, does the number of triangles increase to infinity or does it decrease to 0? And actually, neither of those answers are correct. It has some limiting expectation. So you get some finite, when the number of vertices is very large, you get some finite expected number of triangles in your graph. And to improve our understanding even more, we could look at the random variable which counts the number of I cycles. And you can actually show that that's asymptotically Poisson with the mean that I wrote here, 2 to the I over 2I. And if you look at different ones, then they're independent. So anyways, that gives you some indication. The way I think about this is if I look at any 3 vertices, the chance that they're part of a triangle, that they span a triangle, decreases as I increase the number of vertices. But I have more triples of vertices that might give triangles. And somehow this is saying that those 2 competing phenomena balance each other out. And I get a finite non-zero expectation for the number of triangles and the number of squares and the number of fivegons, etc. So those are sort of some preliminary questions. A deeper and more important question has to do with how hard it is to cut the graph in 2. So here I've drawn a 3 regular graph that's very easy to cut in two. You just cut this middle edge, and then you get 2 chunks of approximately the same size. And a related question is, how fast does the random walk mix? So when you're thinking about that question, you start at a point, a vertex, and then with probability 1/3, you move to each of the 3 neighbors. And then with probability 1/3, you move to each of the 3 neighbors. And you ask, how many steps of the random walk do you need to have some definite probability of being at any given vertex? They call that the mixing time of the random walk. And if the graph is easy to cut in two, it will actually have large mixing time, because somehow there's only one bridge from the one half of the graph to the other, and it might take the random walk longer to find that bridge and cross it. So if there's a single bridge like this joining 2 halves, it'll take the random walk longer to mix, longer to go everywhere. And you study both of these questions quite simply using linear algebra. So you define the adjacency matrix as the square matrix of size equal to the number of vertices, with a 1 in position ij if there is an edge from vertex I to vertex j. So you have to number the vertices, but it doesn't matter how you do it. And this gives you the symmetric V by V matrix, where V is the number of vertices. And often graph theorists and probabilists work directly with the adjacency matrix. For my purpose, I'd like to instead work with the Laplacian of the graph, which is just a shifting or recentering of the adjacency matrix. So you take the identity matrix, this I is the identity matrix, and then you subtract 1/3 times the adjacency matrix. So 1/3 times the adjacency matrix is, of course, the matrix that gives the transition probabilities for the random walk. So you're just taking the difference with the identity. And the main effect of this is it shifts the eigenvalues. So if you look at the constant function, because it's a 3 regular graph and we used 1/3 here, the constant function is in the kernel of the Laplacian. And so that corresponds to the eigenvalue lambda 0 equals 0. And then the other eigenvalues are bigger than 0 if the graph is connected. And you get the spectrum, so you get the number of eigenvalues is the size of the matrix, which is the number of the vertices. So we're going to be interested in the spectrum, and it's of course trivial to shift the spectrum back and get the spectrum of the adjacency matrix if that's what you prefer. But for comparison with the case of surfaces, I want to use the Laplacian. So one of the simplest to state results is about what's called the bulk distribution of the spectrum. And it says that the proportion of eigenvalues in an interval, so as you increase the size of the graph, you pick a random 3 regular graph, it's typically close to the weight assigned to this interval by an explicit distribution supported on this interval. And I've drawn a graph of the distribution. This is what's called a Keston-McKay distribution. It was discovered by McKay and independently by Keston at about the same time. And it's quite different than the semicircle law you might expect from random matrix theory. And it's supported on this interval. This number 1 minus 2 square root 2 over 3, that's a small positive number. So it's quite interesting that the support does not include 0. So the spectrum lambda 0 is at 0, and all you know a priori is lambda 1 is bigger than that if it's connected. But the support doesn't include that. But what does this mean? So the proportion of eigenvalues, so that means you fix some interval and you count the number of eigenvalues in that, and then there are V eigenvalues total. V is the number of vertices. So you take the number of eigenvalues in this interval and you divide it by V, and that converges to the weight of this interval in this probability distribution. So if you picked the interval from, say, 0 to this number, it wouldn't tell you that there are no eigenvalues less than 1 minus 2 over square root 3. It would actually tell you that there are little o of the number of vertices because you're using proportion. So this leaves leaves room for small eigenvalues, but in a sense, not that many. Most of the eigenvalues, in a naive sense, are bigger than this small positive number. Okay, but actually we care especially about lambda 1, which somehow isn't, we don't get that much information about lambda 1, the first non-zero eigenvalue. And we care about that because the Chiger constant of the graph, so I'm not going to define Chiger constant, but it's something that measures how hard it is to cut the graph in two. So the Chiger constant is related to lambda 1, and the mixing time is very transparently related to lambda 1. Essentially, the bigger lambda 1 is, the faster the random walk mixes, and the harder it is to cut the graph in two. So you want lambda 1 to be big. And actually, given a sequence of graphs with lambda 1 bounded from below, you call that sequence an expander. And of course, the study of expanders is a huge topic spanning many different areas of mathematics and computer science and engineering. They have enormous applications. It's very desirable to have, say, 3 regular graphs or deregular graphs that are expanders. And you want the best expanders you can get. So you want lambda 1 to be as big as possible. So the main theorem in this context is that for random, say, 3 regular graphs, typically lambda 1 is bigger than this same number, 1 minus 2 square root 2 over 3 minus epsilon. And this doesn't follow from the old result on the bulk. The result on the bulk of the spectrum just said that most eigenvalues are bigger than 1 minus 2 square root 2 over 3. This actually gives you that all the eigenvalues are typically bigger than 1 minus 2 square root 2 over 3 minus epsilon. So again, a more formal statement would say that for all epsilon, the probability that lambda 1 is bigger than this number goes to 1 as the number of vertices goes to infinity. And this is a very deep result. The paper is extremely long. I haven't read it. I'm told it's very difficult. It certainly took a long time to prove. It was a 1986 conjecture of Alon that had received considerable attention. What's much easier, though, is to say that you can't do much better than this. So actually, all 3 regular graphs with enough vertices have lambda 1 less than or equal to the same quantity plus epsilon. So you can't improve this number 1 minus 2 square root 2 over 3. You can't even find any large graph with lambda 1 significantly better than that. So what this result of Friedman that proved this conjecture of Alon is saying that typically random 3 regular graphs are near optimal spectral expanders. Just as context, you actually can hope for better than near optimal. A typical definition for optimal is you remove this epsilon. So if you actually have lambda 1 greater than or equal to 1 minus 2 square root 2 over 3 with no epsilon, these graphs are called Ramanujan. And the construction of Ramanujan graphs is, of course, also big business. And just to give you an idea of the ongoing story in graph theory, it's conjectured that a definite fraction of random 3 regular graphs should be Ramanujan. But that's wide open, and there's even some disagreement about what the fraction should be. So it's not all of them. It's not typical, but there should be some definite probability that a random 3 regular graph is Ramanujan. But that's a very difficult open problem. So these results on lambda 1 can actually be quite difficult, even in the setting of graphs. So by the way, are there any questions so far? No questions? Okay, well, in that case, I'll continue. Please just unmute yourselves and feel free to ask if you have questions at any point. I'm very happy to get questions. So that was a brief summary of some of the results that are known for graphs. Many other results are known. I just picked some of them to talk about. We want all analogs of all of these results for random surfaces. And of course, instead of a large number of vertices, we want large genus. But we have to confront the fact that there are infinitely many hyperbolic surfaces of any genus, at least 2. And in fact, the set of hyperbolic surfaces of genus G is infinite. So it's not only infinite, it's a 6G minus 6-dimensional real manifold, or actually it's an orbifold, but we can gloss over that point. So it's no longer clear how to define a random surface of genus G. It's not, before we just had a finite set and it was extremely natural to put the uniform probability measure on it. Now we have an infinite set, this 6G minus 6-dimensional manifold, and it's not clear how to define a random surface. And so what I want to do now is just take 5 minutes and go over for you some of the different ways that people have proposed to model random surfaces of high genus. So the first is the random graph model, which I essentially alluded to earlier. So you fix some cuff length L greater than 0 once and for all, and then you generate a random 3-regular graph, just uniformly at random, and then you glue together a bunch of pants with those cuff lengths with the gluing pattern given by that 3-regular graph. And I think that's one of the most natural models that goes back at least to Buser in the 70s and 80s. The idea, I think it really goes back much longer, the idea of building a surface following the pattern of a 3-regular graph. A more sophisticated variant on that is a model due to Brooks and Makeover. And in this model, you again produce a random 3-regular graph, but instead of gluing pants, you glue triangles. And this might be a little hard to understand for non-experts, but I'll at least say briefly that actually what they do is they glue ideal triangles, and that produces a surface with cusps, and then they conformally compactify the cusps. But anyways, you don't have to understand any of that for this talk. This isn't a talk about the Brooks Makeover model. It suffices to know again, they're generating a random 3-regular graph, and then they're gluing, in this case, triangles together to get a surface. And then, if you want to move a little bit away from 3-regular graphs, another very good idea for how to build a random surface is you fix some base surface, maybe a hyperbolic surface of genus 2, and then you just take a random cover of it, say a fixed degree. So what these models have in common so far is in all of them, you have a finite set. So the finite set of 3-regular graphs, or the finite set of degree D covers. And then you just pick uniformly at random from the finite set. And that has the advantage of being elementary and very clear and really very natural. But it also has some disadvantages. It really doesn't, none of these models really see the fact that the space MG of genus G hyperbolic surfaces is infinite. Each of these only really see finitely many points in this huge 6G minus 6-dimensional manifold. And so you might ask yourself, well, if all I'm doing is producing finitely many points in this 6G minus 6-dimensional manifold, is that really an accurate representation of a random point of this manifold? And actually, I think it is pretty decent, but it still leads to the question, is there a natural tractable probability measure whose support is includes all genus G hyperbolic surfaces? That would be interesting to have that, and then to compare it to these other models. And of course, it's key that it has to be natural to really have us feel like it's meaningful. And then, of course, we have to be able to compute with it. It's not very useful to define a model if you can't prove any theorems for random surfaces in that model. But of course, I wouldn't bring it up if the answer was no. There is a natural tractable model, and it's given by the Weil-Petersen measure on the moduli space of genus G hyperbolic surfaces. And its study in the context of random surfaces was pioneered by Mirzakhani, and she actually devoted her talk in the International Congress of Mathematicians to the topic of Weil-Petersen random hyperbolic surfaces. And I want to tell you what it is. It's miraculously easy to describe. It's based on the notion of Fenchel-Nielsen local coordinates. for this moduli space of surfaces. And this brings us back again to pants. So let's say I fix a point in MG, which in other words means I fix a hyperbolic genus G surface X. And I want to produce local coordinates near this point for the moduli space of hyperbolic surfaces. So let me consider a pants decomposition, which you can think of in different ways. One way is it's a collection of 3G minus 3 disjoint simple geodesics. When you cut these geodesics, you get a collection of 2G minus 2 pants. Okay, so a pants decomposition is nothing more and nothing less than a way of cutting up your surface into pants. There are 3G minus 3 cuff curves. And just by thinking about their lengths, you get 3G minus 3 local coordinates that are the lengths of the cuffs. But I said that MG, this moduli space, is 6G minus 6 dimensional. So we're still missing 3G minus 3 local coordinates. And these are called twist coordinates, and they keep track of how you glue the pants together. So if I have two cuffs of the same length, I can glue them together. But there's actually a one-dimensional family of ways of doing this. I can sort of twist before I glue. So here I've illustrated the effect of twisting about this red curve. I cut it and then I re-glued it with a different twist. The blue curve is just there as a reference point to help you keep track of what's going on. So there are these twist coordinates that keep track of how you glue the cuffs together. And in total, the 3G minus 3 length coordinates and 3G minus 3 twist coordinates give 6G minus 6 so-called Fenchel-Nielsen coordinates. And these are indeed local coordinates for the space of hyperbolic surfaces. And these are a very central topic in Teichmuller theory. So that's great. It's very simple. We do have to confront, however, that actually each surface has infinitely many pants decompositions. So that means that each point in the moduli space is contained in infinitely many local coordinate charts. But there's this absolutely magical fact due to Wolpert that the standard volume form is well defined. So if I look at a Lebesgue measure in one coordinate chart, it's the same volume form as the Lebesgue measure in another coordinate chart. So I just sort of wedged together all of the different Fenchel-Nielsen coordinates, and that's invariant under the change of coordinates. And this is, so it's a consequence of what's called Wolpert's magic formula. It's so magic, people actually call it the magic formula. But it says that, essentially in this is the most common system of local coordinates. It says the standard Lebesgue measure is well defined in this system of coordinates. Okay, so it's magical. So you can imagine if this is magically well defined, it's quite meaningful to think about this volume form. And I should say, of course, that the total volume of the space is finite. So I could normalize this Lebesgue volume form to be a probability measure, and then I could pick a random point with respect to this. It's essentially just with respect to Lebesgue. So what I'm saying is there's a canonical, miraculously well-defined Lebesgue measure on the moduli space. And it's every bit as natural as Lebesgue measure on Rn. And in local coordinates, it is literally just Lebesgue measure on Rn, or R6G minus 6. So if you pick a random surface according to this Weil-Petersen probability measure, you'd call that a Weil-Petersen random surface. And Mirzakhani she really pioneered the study of Weil-Petersen random surfaces, which in a sense is different than the previous models in that this measure sees the whole moduli space. Its support is all genus G surfaces. It doesn't have finite support. Okay, so anyways, that's 4 different models of random surfaces. There are even more than that, but I don't want to overwhelm you. So back to the main question, what does a random surface of large genus look like? And so a priori, you might get a different answer in each different model, but reassuringly, the answers to most questions don't depend on the model, or at least they don't depend very much on the model. You get qualitatively similar answers. And that, to somebody studying this stuff, is enormously reassuring, you know, any given model, you could ask, is this the right model? What if somebody else has a better model? You know, maybe you're using the wrong model, and so you're wasting your time. But actually, all the models give similar answers. So it really reinforces the idea that this area is very robust, and you're really somehow uncovering some robust model independent truths if the different models sort of roughly agree with each other. And that is the case. All the different models roughly agree with each other. You know, there are differences. In particular, the difference between using a model that only sees finitely many surfaces is really different than using the Weil-Petersen model that sees the whole space. But qualitatively, they all give similar answers. There are no big surprises. So anyways, we're now well equipped to talk about this question. Back to the beginning of the talk, you can forget about graphs if you'd like, although I'm going to go over analogs of every one of those theorems. But you can forget about graphs if you'd like. We're talking about the question, what does a random surface of large genus look like? Well, again, the easiest result to appreciate is in all the models, the diameter is typically logarithmic in the genus. So for the models that are more closely related to graphs, this follows immediately from the corresponding statements for graphs. In some models, so for example, in this Brooks makeover model, Brooks and Makeover themselves in 2004 proved a coarse version of this result. Very recently, there was a very fine version of this result found where you actually figure out which multiple of log G is typical. In contrast, in the Weil-Petersen model, Mirzakhani proved a coarse result. We still don't have a fine result that tells you exactly which multiple of log G is typical, but we know the diameter typically lies between two different multiples of log G. So the diameter is typically logarithmic. So again, this is in sharp contrast to that linear surface we had with linear diameter in genus. That's very atypical. Actually, the diameter should be logarithmic in G. So if we're going to compare in order to the results on graphs, we should then define this function n sub ab. So given an interval ab, so a and b are positive real numbers. So we have this interval ab in the real line. Then we can let NAB denote the number of primitive closed geodesics. Primitive just means it's not a multiple of another one. You can ignore that detail. So we define NAB to denote the number of geodesics of length in this interval AB for a Weil-Petersen random surface of genus G. So you could start off by thinking of NAB as a function from MG to the non-negative real numbers. But then by picking the point of MG in a Weil-Petersen random way, you can think of this as a random variable. So for each G, you get a random variable valued in the non-negative integers. And this random variable counts geodesics of length in AB, in the interval AB. And then you want to know how many geodesics are there in this length, in this interval. Does it grow linearly? Does it go to infinity? Does it go to 0? You know, what happens? And again, the result is that it as G goes to infinity, there's some limiting mean, which is not 0 and it's not infinity. So you can add, you know, when the genus is high, there's some well-defined positive finite answer to the question, how many geodesics do you expect a length between A and B? So the full statement is as follows. So if these variables should converge to Poisson random variables as the genus goes to infinity with mean given by this value. And if you use disjoint intervals, then you get asymptotically independent random variables. So this is an analog to the result for graphs that counted the number of triangles and the number of squares and the number of phygons. So it's saying you get some finite, non-zero, non-infinite expected number of geodesics in a fixed length. And in particular, this says there's some finite chance of having a small curve, but also a very big chance of not having a small geodesic. So this model sees the fact that some surfaces have can have a small geodesic, a small systole, but it doesn't give them overly high weight. Okay, so anyways, this is a sort of sophisticated result. You don't need to understand the whole result. But I just want to pause now and ask if there are any questions before we go on to talk about eigenvalues.
I just have a small question. What is a primitive geodesic?
It's just so I'll tell you what isn't a primitive geodesic. If you go around twice the same geodesic, that's not primitive.
Okay, and your geodesics are closed.
They're closed, yeah. I should write closed everywhere, but often I forget.
Okay.
Yeah.
So I had a question.
Thank you.
Yeah, Christian.
Uh-huh.
Yeah, I have a very bad question. You talk about different models, but is it interesting to relate the random surfaces from one model to another? Are they related somehow?
It would be wonderful to relate them. We'd all like to relate them. You know, in graphs, I was a little glib before. For random graphs, there actually are some different models, but many of them are, the word is contiguous. So there's some formal definition that basically says it doesn't matter which model you use. We don't know how to directly relate any of the models. Everybody would like to do that. We keep, different groups of people will prove similar results in different models, and we'll say, gosh, these really look similar. I wish we could come up with some a priori reason why we'd have to get the same, at least very similar answers in different models, and nobody knows how to do that. Right now, it's just an empirical fact that the different models seem to give similar answers.
That's a very interesting problem, maybe.
It's very interesting. It would be absolutely wonderful to prove a theoretical result that says, without figuring out the answer, you could know ahead of time that the answer would have to be similar in the different models.
Thank you.
That's actually a very good question.
Are there any other questions for Alex?
Okay, if not, I'll get to really the main topic of this talk, now that we're past the halfway point, is eigenvalues for surfaces. So it's hard to define an analog of the adjacency matrix, but it's easy to define an analog of the Laplacian. It's still called the Laplacian, or if you'd like, the Laplace-Beltrami operator. It's a differential operator on functions. It's absolutely the analog of the usual Laplacian in R2. And its spectrum, at least in the normalization I'm going to use, so it has 0 as an eigenvalue. So first of all, it has discrete spectrum for closed surfaces. It has 0 as an eigenvalue. That's the eigenvalue of the constant function. The constant function is annihilated by the Laplacian. And then if it's a connected surface, lambda1 is greater than lambda0. And you have this discrete sequence of eigenvalues. It's an infinite sequence and it goes to infinity. It's quite reasonable because there's no longer the case that there's a finite number of vertices. So now you have infinitely many eigenvalues. And you're interested in the whole spectrum, and you're also still especially interested in lambda1. It's still true that lambda1 is related to the Chiger constant. So it's related to how difficult it is to cut the surface in two. It's still true lambda1 governs the speed of mixing for the Brownian motion. It governs the speed of mixing for the geodesic flow for the hyperbolic metric. It governs a whole lot of things. And it's still true you want lambda1 to be as big as possible. If lambda1 is big, it's hard to cut the surface in two, and the Brownian motion mixes very fast. The geodesic flow mixes very fast. So you want lambda1 to be big. But before we get to lambda1, let's talk about the bulk. So for the bulk, what you can say is that the number of eigenvalues is in an interval. And here you can't say proportion because there are infinitely many, but you just divide by the genus. So you fix some interval from A to B, and you say how many lambda I lie in that interval. And then you divide by G. And you pick a random surface and let G go to infinity. So if you pick a Weil-Petersen, this WP stands for Weil-Petersen. So typically, if you look at a Weil-Petersen high genus surface, it's typically close to the weight assigned to this interval by an explicit distribution supported on the interval from a quarter to infinity. Okay, so this result was proven this exact result was proven by Monk in 2020. Results of this form go back a very long time, at least to Wallach in 76. The number theorists would call a result like this a limit multiplicity formula. The physicists would call it a density of states result. And the distribution you get goes back to the 70s. It's pretty clear what to expect. So again, you get this distribution. So if I wanted to know the number of eigenvalues between 3 and 4, this function is about equal to 1 between 3 and 4. So I expect about genus, well, maybe I left out some constants, so times some constants. So you expect genus many eigenvalues in any interval, except for the small eigenvalues. If I look at the interval from 0 to a quarter, it's exactly analogous to before. I'm not saying there are no eigenvalues there, but typically you have little o of the genus. So if you look at the number of eigenvalues between 0 and a quarter and divide by g, that's typically close to 0, typically going to 0 as the genus increases. So this result doesn't say that there are no eigenvalues of less than a quarter, but it says you don't expect many of them. Okay, so it's exactly analogous to the result we mentioned before with the Keston-McKay distribution, but now there's this distribution that comes from the tanh, the hyperbolic tan function. Okay, but again, the bulk is very good. We do care about the bulk, but we especially care about lambda 1. And the natural conjecture, which everybody would like to know, is that the lambda 1 should be typically greater than a quarter minus epsilon. So this would be the analog of Hollande's conjecture for graphs. And it's known you can't do better. So this is similar to the Hollande-Bopanna bound from before. In high enough genus, every surface has lambda 1 less than a quarter plus epsilon. So you can't do better than a quarter, not even for a single surface in high genus. So again, this conjecture, you could say it as saying, typically lambda 1 is as big as possible. Typically, Brownian motion mixes as fast as possible. Typically, the surface is as hard as possible to cut into. So it's a very deep conjecture, and it's very much related to a lot of number theory. This is related to Selberg's 1/4 conjecture. Lambda 1, for special arithmetic examples, lambda 1 has a lot of number theoretic significance. So there's a lot of different reasons people arrive at this conjecture from many different points of view. The conjecture is still open in every single model. It would be a big deal to prove the conjecture. Actually, it's only this month, like within the last week, Hill and McGill showed that there's a sequence of surfaces with lambda 1 going to a quarter and genus going to infinity. So if you'll believe it, like before last week, it wasn't known if you could build any surfaces in high genus with lambda 1 close to a quarter, even though it was conjectured that lambda 1 is typically close to a quarter. Right, so it's only this summer that we know how to prove there's a sequence of surfaces going to a genus going to infinity with lambda 1 going to this optimal value of a quarter. And just finding a single sequence like this had been open since '84, and it was only resolved this summer. So it gives you an idea that this conjecture is very hard. So the conjecture is still open in all models, but at least we know there's some high genus surfaces with lambda 1 going to a quarter. And I should say that Hill and McGill sort of did resolve a version of this conjecture, but for non-compact surfaces. But I'm gonna not talk about that too much because I'm really focusing on this in this talk on compact surfaces.
But is there example? Is it a constructive example, or it's just there exists?
So what they do is they look at the random cover model, but for surfaces with cusps. And they prove a version of the conjecture in the random cover model, but for surfaces with cusps. So they produce high genus surfaces with cusps where this result holds. And then they glue the cusps together and sort of serger them so that you just have a short curve instead of two cusps. And in this way, they sort of, via random methods, produce some high genus surfaces with lambda 1 close to a quarter.
Okay,
and
but
for this,
it's constructed.
it's sort of constructive. I mean, they can't tell you one surface in particular, but they can tell you a random procedure to build the surfaces. Yeah. And I should say this is building on very deep work in graph theory. So there's a version of Alon's conjecture where instead of looking at uniform random graphs, you look at uniform covers of a fixed graph. And there, an optimal result was proved like in something like 2017, don't quote me on the date, but surprisingly recently by Bordenhaven-Collins, using some ideas from free probability. And Hill and McGill use those deep ideas. And so it's very deep and technical. It's not a naive analysis. Okay, but I want to sort of focus on what we can understand for typical surfaces. So we're not going to get to a quarter. In the Brooks and Makeover model, Brooks and Makeover showed in 2004 that in their model, at least lambda 1 is typically bigger than some positive constant. I haven't read their paper. I'm told that the constant isn't even explicit at all. Like they show there exists a positive constant without saying what it is. Mirzakhani showed that in her model, the Weil-Petersen typical model, lambda 1 is typically bigger than some constant, which is about 0.002 in high genus. So again, the formal statement would be, as the genus goes to infinity, the probability that lambda 1 is bigger than 0.002 goes to 1. And then my contribution to this in joint work with Mirzakhani was to show that Weil-Petersen typically lambda 1 is bigger than 3/16 minus epsilon. So again, the statement would say for all epsilon, the probability that lambda 1 is bigger than 3/16 minus epsilon goes to 0 as the genus goes to infinity. Or sorry, goes to 1 as the genus goes to infinity. And this result was independently and simultaneously achieved by Wu and Shui. And I should say that another 3/16 result was proved for random covers in the random cover model by McGee, Node, and Puder in 2000. And subsets of these authors also proved a similar result for random covers of non-compact surfaces. So it's interesting, a lot of different people are working on this, and they're all getting to 3/16. And it's not always clear why we're getting 3/16. And people always ask, is it the same 3/16 that Selberg got? And I don't think it is, at least not transparently. Anyway, so 3/16 is a little bit smaller than a quarter, but we can at least show that lambda 1 is Weil-Petersen typically bigger than 3/16 minus epsilon as the genus goes to infinity. So are there any questions about the statement? If not, I'm going to devote the rest of the talk to saying at least a little bit about this, this joint work with Mike Lipnowski. So how do you prove bounds on lambda 1, or really how do you prove anything about the spectrum? Well, it's a little bit easier to say how you do it for graphs. So if you take the adjacency matrix A and look at some big power of it and compute the trace, well, you can compute the trace of a matrix in two different ways. The trace of a matrix is the sum of the eigenvalues. That tells you about the spectrum. And it's also the trace of the trace of a matrix is the sum of the diagonal entries. And for a power of the adjacency matrix, that counts the number of loops of length n in the graph. And so this relates the two, and it goes both ways. But for this application, the idea is if you can understand the number of loops of length n in the graph for appropriate n, then you'll understand lambda 1 and other things about the spectrum. This is the common idea in many different results in spectral theory. So there's a version of this also for hyperbolic surfaces. It's called the Selberg trace formula. I'm not going to state it, but it relates eigenvalues of the Laplacian to primitive closed geodesics, and essentially allows us to reduce the problem of proving lambda 1 is big to understanding the number of closed geodesics. And this is how I came to work on this problem with Mike Lipnowski. Mike Lipnowski is a number theorist. He was a student of Akshay Venkatesh. Number theorists care a lot about the Selberg trace formula. They're extremely good at applying it. And so Mike is an expert on applying trace formulas in various situations. And I have some expertise in Weil-Petersen aspects of moduli spaces. So that's how we came to work on this together. Even though Mike is a number theorist and I consider myself to be either a geometer or a dynamicist. So what you get out of the Selberg trace formula after you analyze it is you end up needing to understand the average number of geodesics, the Weil-Petersen average of the number of geodesics of length at most log g for sort of averaged with respect to the Weil-Petersen measure over the moduli space of genus G surfaces. And if you can do that well enough and you get the right answer, then you get this 3/16 result. And the problem is we don't know how to do that. We don't know of any exact way of computing exactly what that Weil-Petersen average is. But we don't need to compute it exactly, and there's some reason for hope. And the reason for hope comes from Mirzakhani's thesis. So Mirzakhani, of course, famously wrote this spectacular 3-part thesis that was very revolutionary. And one part of that is she showed how you can exactly compute the average number of, for example, simple non-separating geodesics of length at most some number L, averaged with respect to the Weil-Petersen measure on the moduli space of genus G surfaces. So here, simple means no self-intersections, and non-separating just means it doesn't disconnect the surface. You can ignore non-separating. It's a minor issue here. She also lets you do it for separating geodesics, but it turns out it's the non-separating geodesics that are typical. Further work by Mirzakhani and Petri showed that at modest length scales, so say if the length is a lot smaller than square root genus, the average number is about e to the L over L. So averaged over mg, you expect like the expected number of simple non-separating geodesics is about e to the L over L, as long as this length scale is not too big compared to the genus. So this is quite fascinating if you're an expert in this area. And if you're an expert in this area, you'll instantly be comparing this to an old result of Huber that was reproven by Margulis, and it now is very general. But in particular, it says on a fixed hyperbolic surface, the number of geodesics of length less than L is asymptotic to e to the L over L as L goes to infinity. So this is a very famous result that's true in many contexts. So there's about e to the L over L many geodesics on a fixed surface as the length goes to infinity. This is an asymptotic result. And so since it's an asymptotic result, it a priori doesn't tell you anything about finite L, let alone some particular L, like L equals square root G. But still, you might naively use it as a baseline sort of expectation. So if we're being very naive, ignoring the fact that this has only been proven as L goes to infinity, we might extrapolate and say, let's just, as a benchmark, let's say we're expecting about e to the L over L geodesics of any given length, even of like fixed length. Okay, keeping in mind we have to take that with a very big grain of salt. But okay, still you can't help but noticing I have the same number twice, e to the L over L. So somehow, maybe roughly, I was expecting e to the L over L total geodesics, and only looking at the simple non-separating ones, I already got about that many. Okay, so even though this is a little dodgy with the asymptotics, you can't help but finding this very suggestive. And it leads to the following conjecture. So if the length is a lot less than square root genus, then on most surfaces of genus G, most geodesics of this length are simple and non-separating. And then we actually think this is sharp too. If the length is a lot bigger than square root genus, then on most surfaces of genus G, most geodesics of this length are not simple. So again, not simple means it intersects themselves. Okay. So this seems to be interesting. This conjecture seems to be new. it really gives a very evocative picture of how to understand surfaces, geodesics on surfaces with length scales that vary with the genus. Let me just discuss this for a minute before going back. So on a fixed surface, if you look at very long geodesics, very few of them are simple. So if you look at long geodesics on a fixed surface, most of them are not simple. And there's a gazillion ways of quantifying this. You know, if you fix a surface and let like the length go to infinity, a typical geodesic will intersect itself like L squared many times. Or you could cite a result of Mirzakhani that says, you expect the number of geodesics of length L to be polynomial in L, but of course they're exponentially many overall. So being simple is really not typical. And so this is really a very bizarre miracle at this intermediate length scale. So it's like growing with genus, but not too fast. It seems like at these moderate length scales growing with genus, you get the expected number of geodesics, but they don't have the expected shape because they're simple. So it's this sort of bizarre thing. At these moderate length scales, you're getting the typical asymptotic answer for the number of geodesics, but with geodesics that are very weird compared to what would happen if you fixed the surface and let the length go to infinity. Okay, so it's a sort of weird conjecture, but this is it. At moderate length scales, most geodesics should be simple. So we don't actually prove this, nor do we need it, nor would it really help, but it very much will help you understand what we're doing. So we need essentially some sort of average statement along these lines because we only need to know the average number of geodesics. And we're working at the log G scale, which is reassuringly a lot smaller than square root G. By the way, Mirzakhani, Petri did something similar, but they worked at bounded scales. They proved the Poisson approximation result, and their paper very much inspired ours. So we're going to prove an averaged version of that conjecture at the log G length scale. But we should keep in mind that what we're doing is not soft, it's hard analysis. The whole name of the game of the error term is the error term. You spend all of your time paying attention to the error terms. Basically, what we want to do is show that there's about e to the L over L, that the average number of geodesics is e to the L over L with very small error. And if you get better error, you can replace the constant 3/16 with something closer to a quarter. If you get really exceptional error, then you can prove the 1/4 statement. So it's all about the error term. For us, it wouldn't help to go past the log G length scale. It's best to stick to the log G length scale. But you have to care a lot about the error term. So just a quick recap here. To bound lambda 1 using the trace formula, we want to know the average number of geodesics of length at most C log G. Mirzakhani tells us that the average number of simple geodesics of this length is about e to the L over L. And we suspect or conjecture that most geodesics are simple. So in essence, we need to prove this statement, how to prove that most geodesics are simple, or to rephrase that, how do we prove that there are few geodesics that are not simple? Well, there's a central idea that was introduced by, that was used in particular by Mirzakhani and Petri. And the idea is that every geodesic is either fills the whole surface or it fills a subsurface. And a geodesic fills a subsurface if its complement in the subsurface consists of simply connected polygons and some annular regions about the boundary. The case of a simple geodesic is very special. You might say a simple geodesic fills an annular subsurface, but let's maybe put that aside. So the idea if it's not simple, it intersects itself and it might not fill up the whole surface, but it at least fills up some subsurface, sort of combinatorially. And it turns out that a geodesic at the logarithmic length scale is way, way, way too short to fill up the whole surface. That's essentially the isoparametric inequality. So these logarithmic sized geodesics are going to fill up fairly small subsurfaces. And so the main idea in the paper of Mirzakhani is to do a sort of accounting or bookkeeping where you say, I'm going to keep track of the number of geodesics by keeping track of how many subsurfaces there are and then how many geodesics each subsurface has. And so the key new input we need is a bound on the number of geodesics per subsurface. And we don't have to do this for every subsurface, only the subsurfaces that typically appear. So we do it for what you might call tangle-free subsurfaces. And we prove a result that you might paraphrase by saying a tangle-free subsurface has very few closed geodesics. And I'll tell you what tangle-free means on the next slide. The key point, though, is it's an analog of a definition used for graphs. So the precise definition of tangle-free is easy. It means no pants or one-hole tori with boundary less than some constant. And for typical surfaces, the constant can be taken to be very large. So what we get is that typical surfaces in MG, for the subsurfaces we care about, they have very few geodesics that aren't simple. So just to give you a quick final summary, we want to show that Peterson typically lambda1 is bigger than 3/16 minus epsilon. The proof goes as follows. The Selberg trace formula relates closed geodesics to spectrum. So we need to understand the geodesics of length, a certain scale that's growing slowly with genus, this log G scale. There are an understandable number of subsurfaces that these geodesics can fill. And each such subsurface has few geodesics. So it suffices to use Mirzakhani's count of simple geodesics. And this gives us a sufficiently good understanding of the average number of geodesics. So that's an outline of our theorem, and that concludes my talk. Thank you for your attention.
Thank you very much, Alex. We thank Alex for the beautiful talk and very interesting.
Yeah, splendid talk.
Thank you.
But not simple.
Are there any questions?
A question?
Yes, please.
So you've concentrated on the first eigenvalue. Do you know anything about the rest of the spectrum?
Well, we have this bulk result, this result of Monk that I mentioned, that gives you the bulk of the spectrum. But you could also, so you call eigenvalues less than a quarter small, and you can obtain bounds showing. So this result says that the number of small eigenvalues is little o of G. You can do better than that, and actually Monk did better than that. Yeah, so basically you divide it up into the small eigenvalues and the eigenvalues bigger than a quarter. But there's so many open questions. For example, there are these heuristics that suggest that eigenvalues should typically repel each other. So you can ask about eigenvalue spacing. Basically everything about eigenvalue spacing is open. There are so many different results that are open. I think hopefully we'll see a lot of progress over the next decade.
Okay, thanks, Sam. Fascinating field.